In this problem, what it deals with is it deals with determining the wavelength of lines of the X-ray portion of the spectrum. All right, so what we want to do is we're going to determine what is the wavelength of a couple lines in the X-ray spectrum from tungsten. So the problem reads as such. The element tungsten has an atomic number of 74. So since it has an atomic number of 74, then Z is equal to 74. And it asks us to calculate the wavelength of the K alpha and the K beta lines of the characteristic X-rays. All right. So the equation we're going to do, and we want to find, we're going to finding EK. So to find the EK line, the equation we use is a negative 13.6 electron volts times, this is going to be Z minus 1 squared, all divided by N squared. This is basically going to be the orbit. So K is going to be the first one, KLM. This is going to be the first one. So for K, our N is going to be equal to 1. And so for this one, we simply plug in 74 into this. We still have a negative 13.6 electron volts times, this becomes 74 minus 1 quantity squared divided by 1 squared, and that's going to be equal to a negative 72,474 electron volts. Likewise, we're going to now find EL, and that is going to be where our N is going to be equal to 2. And so this is a minus 13.6 electron volts times, it's still tungsten, so we have the exact same atomic number. So this is going to be 74 minus 1 squared divided by, this becomes now 2 squared. We go through and we do this arithmetic, and we end up with a minus 18,118 electron volts is what we get. Now, if we take EL minus EK, all right, so EL minus EK is going to be a minus 18,118 electron volts minus a negative 72,474 electron volts. Then what we end up getting is we get 54,355 electron volts, or we can say this is going to be equal to, it becomes 54.4 kilo electron volts. Now, what we want to do is we want to convert this into joules, something we can manage a little bit better. So we take 54,355 electron volts, and we say that for every 1 electron volt, that's equal to 1.60 times 10 to the negative 19th joule. So electron volt is the voltage of 1 electron. We know the energy of the electron, so this will cancel, and what we end up with is this becomes 8.7 times 10 to the minus 15th of a joule. All right. Now, recall that E equals hc over lambda. Or we can solve this for lambda, and our lambda is equal to hc all upon E. H is going to be Planck's constant, which is 6.626 times 10 to the negative 34 joule, times the speed of light, which is 3 times 10 to the 8th meters per second, divided by the energy we have here, which is 8.7 times 10 to the minus 15th of a joule. The joules cancel. I'm sorry. I forgot a unit. Don't ever want to forget a unit, right? This becomes times joules second. I'm just going to write this just a little bit better. This is why I got to write the units. This is a joule second. There we go. So the joules cancel, the seconds cancel. And what we end up getting here is we get 2.285 times 10 to the negative 11th meter, or we can say this is going to be equal to 0.0228 nanometers, which is going to be the wavelength for the K alpha line. Now for the second part, I've kind of run out of board space here, so I'm going to erase the board space, and we'll go on and determine the K beta line, okay? Now we're back. We're still going to be working with the EK line, right, which would be the first line. Now we want to find the E beta line, or the K beta line, and so we're going to look at K or EM, and that's going to be the next one. And for that equation, we're going to use the exact same equation, which is going to be a minus 13.6 electron volts. Still, we're dealing with tungsten, so it's going to be 74 minus 1 quantity squared. However, our N is going to be the next one. Remember, we had the EK, which is going to be at the first orbital. EL is going to be at the second orbital. This will be at the third orbital. And this gives us a negative 8,052 electron volts. And so we're going to take EM minus EK, which is equal to a negative 8,052 electron volts, minus the EK line, which is a negative 72,474 electron volts. And that is going to be equal to 64,421 electron volts. We're going to convert that into joules. And so we take the 64,421 electron volts, and we can say that 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. The electron volts cancel. And this is going to give us 1.03 times 10 to the negative 14th joule. Once again, we're going to use E equals HC all over lambda. And our lambda is equal to HC all upon E, which is equal to 6.626 times 10 to the negative 34 joule second. I didn't forget the second. Times the speed of light, which is 3 times 10 to the 8th meters per second, divided by now our energy that we just found above, 1.03 times 10 to the minus 14th joules, or joules cancel, seconds cancel, we're units of meters. We go through and do this arithmetic, and we find out that becomes equal to 0.0193 nanometers. This would be in meters. I already converted into nanometers. And this is going to be equal to our K beta line. Now, if you remember, this wavelength is a little bit smaller than the wavelength of the K alpha line. And that's because the K beta line is for the orbitals, you're going from the third to the first, is further away than going from the second to the first, which is what we saw with the K alpha line. So the K beta line is going to be more energetic because you're going from the third all the way down to the first in the tungsten atom. If you have any questions on this, please let me know.